Is it really significant? I would like to offer a test to find out if this kind of bump or jump in the pricing kernel is significant or not. Yeah, please.
Can you look at this only for the index or also for
yeah, so far we just looked at the index. Don't have other data. We haven't looked at other data. Yeah, but I think it's no problem to look at separate stocks.
No, it shouldn't be a problem. It might look different.
Might look, but we just took the data for the DAX so far. We looked at the DAX at 4 different dates. So in 2000, 2002, and 2004. And at the end, I'll show the results. We found the evidence of non-concavity in utility functions. So we found, for example, in 2002, the monotonicity was significantly rejected. Yeah? And at the same time, in 2004, it was accepted. So it kind of proves the paper of Giacomini and Herdler that the structure of pricing kernel might change in time. Yeah? But this is only for the DAX index, if referring to your question. Your question?
So I'm not quite sure that I understand what is the x-axis here. What do I see?
This is the returns here. Yeah, so DAX returns. And
DAX returns.
yeah.
But the utility should be evaluated at the optimal terminal value, which one could look at as the overall endowment at time capital T. Why do I observe this at time lowercase t? This is what how can we plot such a thing?
Well, I have some time constraints, but this was explained in the presentation of Ruslan Mora, who was explaining how this utility function is obtained from pricing kernel. Yeah? So I'm just taking this pricing kernel and test it for monotonicity. It's exactly one part of this job. Yeah? It might of course be different procedures how we can derive from pricing kernel utility function, but this is the main idea what we'd like to do.
But you don't think this is the estimation procedure that causes this? That somehow you differentiate with respect to strikes, and you have discrete data, and you're basically this is the second derivative with respect to strikes.
Right.
You don't think that's the problem?
Well,
because you have discrete.
Yeah, we are discrete, of course. This is the data. That's why.
The testing procedure. Do you count for this error in estimating?
Well, we'll see. I'll explain how we're going to test for that. Yeah, we just taken this. We're not actually referring to utility function. Yeah? I'm here only motivating why we need to test for monotonicity. Yeah, but in the test procedure, we don't refer to utility function at all.
But you take ratio.
Yes, we take ratio, and in this ratio, the dominator is unknown, and nominator is unknown, and dominator is unknown. Yeah, so that's the main problem that we have. Once again, here is a pricing kernel. Yeah? Q is a risk neutral density. P is a subjective density. Yeah, Q can be good estimated because we have a large number of observations in derivative market. Q corresponds to a replicating hedge strategy that we can construct at any point at T. Yeah, and P, we don't know P. In my case, as I said, we cannot estimate it correctly or more or less correctly. Yeah. Exactly. We have only time series of observations, and P can be estimated only if we know the data generating process, which is not enough to make a good estimation. Yeah. Yeah.
You can follow any probability law that P captures the probabilistic property of the stock price.
Exactly. Yeah.
So it can be estimated.
Can be estimated, but still it's.
As far as I know, you first feed the Garch model into the data.
Well, they try to fit it to Garch model, but could be used also some different models. Yeah. So the main difficulty of test.
So on these figures that you are showing in the next slide,
Yep.
you have already this pricing. So what was the P estimated there? Was it the Garch or Preston?
Exactly. Here we used we estimated Q from derivative option market, like here as well. Yeah. So this is the same Q, the same risk neutral density, and then the difference is in P. Yeah, the difference is in P. Here it's log normal generated from Black and Scholes model. Yeah, and here it's estimated non-parametric, as just you said. We just took the historical time series and make a non-parametric estimation of it and observe this kind of bump. Yeah? But the question, of course, if we don't know if this estimation is good or not. We think that it's not quite precise. Yeah? We'd like to test if this kind of bump is significant or not, because we observed it not only in 2004, but we also observed it in 2002. And
I mean, if you're saying that your estimate is non-parametric.
yeah, that for this picture.
Estimated like an IID returns and put some non-parametric.
Yeah, exactly. That's how it was.
P is based on the year's data, Q based on today's data.
Yeah.
Q is based on 1 day.
Q is based only on 1 day that we obtained from exactly from derivative option data, yeah, from option. Okay, so we go further. So statistically, the problem looks like this. For increasing sequence of DAX returns xk from x1 to xn, we'd like to find out if there exists an interval AEG such that the ratio of pricing kernel k defined as the estimated q and unknown p is not monotone decreasing. Yeah, so the main problem here, of course, is that we consider p unknown and q estimated. And this was the motivation. And we will proceed as following. So I'll just briefly explain the test idea that we described in our paper. So first, we reduced our problem to simple exponential problem using Pike's theorem of order statistics. Then, having it analytically exponential model, we can construct a likelihood ratio test for a fixed interval. Then we expand this kind of fixed interval likelihood ratio test to multiple tests, which is independent of any intervals, using a test intersection procedure. In this section, in this step, we also find critical values using Monte Carlo simulations, and finally, we take the decision about the monotonicity of pricing kernel by comparing the critical values from Monte Carlo with the test statistics obtained from observed data. That's the test outline, and we start with step 1. So let's consider the uniformly distributed random variables u1, un. Then we can define the spacings sk, or uniform spacing sk, the difference of two adjustment values uk minus 1. And then, according to the Pike theorem 1965, we can say that the uniform spacing sk is approximately distributed as the IID standard exponential distributed variable ratio of IID standard exponential distributed variable to the sum of the IID exponential variables. And for a significantly large number of n, we can also use the fact that the expected value of IID exponential variable is 1. So we obtain the first simplification result that n times the uniform spacing sk is approximately IID exponential random variable. Here? Yeah, here. Okay, yeah, I'll check it, thanks. All right, so for the next simplification result, we take a cumulative distribution function px, which is associated with unknown historical density px, and we can use a Taylor approximation for two adjustant returns xk plus 1 and xk, and then as a difference, the uniform spacing sk, we obtain that it's equal to the PDFP times the difference of two adjustment values xk plus 1 and xk. So then when we come to the main simplification result, this is basically the idea of the test. We combine the Pike's theorem of order statistics with the second Taylor approximation procedure, and we obtain the following result. On the left part, we have observed values, which we define as zk, n times known risk neutral density q, times the uniform spacings of our DAX returns xk plus 1 minus xk. On the right part, we have our pricing kernel k, which is unknown, times the IID exponential distributed variables ek. So we would like to check monotonicity of our pricing kernel k using the simple exponential model zk, observed values of zk equal to the pricing kernel k times IID exponential variables ek. Then we can formulate a testing hypothesis and construct a likelihood ratio test. For a fixed interval ig, let R be the set of all positive possible decreasing sequences. Then the nested or reduced model hypothesis H0, K is a monotone decreasing function and K belongs to A on the interval ig. And alternative hypothesis H1 is an arbitrary function, which includes, of course, monotone decreasing function. So we construct a likelihood ratio test for this purpose, which is a classical likelihood ratio test. We compare the maximum likelihood of a reduced model with the maximum likelihood of the general model, and if we do not observe any significant improvement in the likelihood, then we should probably accept H1, and if the likelihood for the nested model is significantly larger, then we should accept H1 of monotone decreasing function. For simplicity, we also perform a monotone transformation here, take a logarithm of our ratio of maximum likelihoods, and using this main result of the exponential model that zk is equal to the pricing kernel k times the exponential ek, we can derive a likelihood function, log likelihood function, which looks like this, which gives us analytical result for the maximum at zk, at k equal to zk, and equal to this kind of formula. Which is much more tricky is to compute the maximum of reduced model when k is monotone decreasing function, and this is performed with the help of Newton-Raphson algorithm and projection on decreasing sequence AEG. This kind of projection we tried to do with the help of isotonic regression, which means that at each time we build isotonic regression and optimize the values with a Newton-Raphson algorithm. So the maximum of our H0 hypothesis that K is actually a monotone decreasing function and belongs to A is reached as an isotonic regression at this point. So this is most time-consuming step in the test, because the maximum likelihood for general model, for general class of models is given analytically, so it's no problem to compute it. But the question is, of course, how to compute the maximum likelihood of this model. Yeah? And this is done with the help of isotonic regression, which can be seen in this picture. Yeah? So we just generated different zk, and with the Newton-Raphson algorithm, we try to find the best isotonic regression which gives us maximum likelihood. And this usually a stepwise function here. That's the red one. This is a optimal isotonic regression that gives us maximum maximum likelihood. Everything is good so far, but this was good only for one interval, for interval ig. Now the question is how to make an independent test, and this is done with the help of so-called test intersection. So we're looking for a minimum critical surface, yeah? So that the hypothesis, the H0 hypothesis, is rejected when it's rejected at least at one of the intervals ig. That's exactly what's described by this minimum ig. So we're looking at all intervals at the same time, and if it's rejected at least at one interval, then H0 hypothesis of monotone decreasing function is rejected overall. Unfortunately, the analytical solution to this equation is very difficult, I would say unknown, and that's why we use Monte Carlo simulations to find the reasonable space of critical values. That's exactly what we do on the next slide. We generate the worst non-increasing sequence k as a constant, still kind of monotone. Yeah, this sequence of constants k1 to kn equal to 1. And then using the main result that we obtained in the first part of the talk, we get that zk is approximately exponential ID variable. Then using Monte Carlo, we can calculate test statistics over different simulated zk, as I identified before, the log of the ratio of two maximum likelihoods. So this is given analytically, as I said, and this is done with the isotonic regression together with Newton-Raphson algorithm, most time-consuming step. Then we also define the mean and the variance, mu and v as standard. And then we find the and we find critical values T alpha as the root of this equation. So we are looking for our reasonable critical surface is given by simulated mean minus the critical value T alpha times the variance of simulated test statistics V for each interval Ig. So this looks like a big matrix Ig, and with the Monte Carlo simulations, we try to find the best value T alpha as a solution to this equation. So we implemented so far this procedure, but it didn't really give us a good power of the test. So it worked, but not always. Sometimes we increased the slope of artificially generated data, and it wasn't identified by the test. So we made some modification, which is introduction of the block, which means that the function, so far we thought the function, the H1 hypothesis, any kind of function, but now we allow the function to be monotone on some block of size B, and then compare not each observation, but compare only the averages of each block. So this is the basic idea. So this block parameter is a trade-off between the variance and the shift of the test statistics. That's what exactly you can see on this picture. Yeah. So the red line is what we had before block. The dashed blue line is what after the introduction block. So we were able to decrease the variance by taking the average of these intervals. Yeah. And this shift is caused by increasing the slope. And so we increase the slope from 0 to some positive slope of the data. So it should be, of course, identified by the test, yeah, because it's not anymore on monotone. And this is exactly that we have, shift of the test distribution. The shift in case of block is a little bit smaller, but the variance is also smaller. So with this block parameter, it works a little bit better. On the right figure, we see what's the influence for different block parameters. So if the block is too big, so if we take, for example, only 2 averages, then it's of course not so good as well. But I have to, this is already explained, just instead of taking each value, we take the average for each block, and then the hypothesis about the test is just a sequence of different surfaces for each B. So I'll just make a very short summary of the test. So first we compute the Z's, which is given to us, n number of observations, Q is estimated risk neutral density, this is DAX returns. Then we compute test statistics, which is given by the log ratio of two maximum likelihoods. This is given analytically. This is calculated with the Newton-Raphson algorithm plus isotonic regression. And then we take decision if at least on one interval Ig, at least for one block size B, this surface is less than 0, then K is not a monotone decreasing function. I think I have to stop now, and the results will be in my paper, because we have still a second presentation of Szymon. Yeah, sure. Yeah, so I'll just show you how the results look like. This is how we make a decision about the monotonicity. So we build a whole sequence of different surfaces, the so-called test surface. This is our simulated statistic C from observed data. This is simulated mu, which we do with Monte Carlo, this mean of the different statistics. T alpha is also, we use a dichotomic method, just split into halves, and then we find the reasonable T alpha. V is also obtained from simulations. And if this surface is under the zero level, which means it's not monotone. If it's above zero surface, then it's monotone. This is just the results. We found that in 2004, it's the empirical pricing kernels were more or less monotone, but it's significantly rejected in 2002. You see the values is very negative. Yeah, and the situation in year 2002 is on the edge. So for 5%, the hypothesis was not rejected. For 10%, we rejected monotonicity of pricing kernel in 2000. See?
If my understand is correctly, you basically said that you have an exponential distribution with unknown mean, and you are testing if the mean is monotonic or decreasing, and you construct complicated test statistics. Am I correct?
Well,
and actually, let me get more straight to the question.
okay.
How do you know the null hypothesis? The null distribution doesn't depend.
We don't know the
Yeah, so you said it, let me make it worse, everything equal to k. I mean, you could also say, I could be also 1, 2, 3, not sorry, 1/2.
Yeah, sure, but
So
it doesn't change the situation.
How do you know it doesn't change?
No,
You
no.
know it doesn't change.
No, I mean, if it's a constant, then if you look, I don't have much time, but you mean if we could of course take here not 1 but some other number, yeah. But it won't change. It won't change the maximum likelihood. Because
I could take it also, I mean, and if decreasing sequences.
Yeah.
Also null hypothesis. Are you sure it doesn't change?
if we take a decreasing sequence, of course the critical values will change. Yeah, but that's why we take the worst, which the constant.
So you're not testing worse, you're testing equal, constant.
Yes. That's correct. Actually, this is one of the weakest points because what we should have done is take the historical observations and from this historical distribution then build these critical values. That would be correct, of course, yeah. But we don't have enough data, so we take this to the constant and look at these critical values for this worst case of a monotone decreasing sequence. Yeah. Yeah.
I probably should have asked this question
Mhm.
yesterday, but I still don't understand. If this thing isn't decreasing, then what is the implication of that? I mean, is it an arbitrage, or is it just means what does it mean?
Well, I think this is a question to Ruslan more than to me. Yeah, but I mean, I'm just taking the results from his paper and try to create a constructed test. Yeah.
Just imagine when margin utility is high, just based from simple economic theory that 1 unit of consumption is valid for more in this state of the world. For best state of the world, 1 unit of consumption is valid for more than the good state of the world. And that really defines here is defined in terms of the terms, because we can think if we look at the DAX index, so DAX index somehow measures the state of the economy. So DAX is high, the economy is prospering, or returns a high economy is doing well. DAX is declining, the economy is getting worse, it's doing worse. So
But you could also say the hypothesis that prices are set with respect to some utility functions.
I'm not saying it's our hypothesis.
I think we need the second file.
Voice, and I think I may start. I try to keep it short because we are running out of time already. The title of my talk is Skew Hedging, and the title of the conference is The Semi-Parametric Meets Mathematical Finance. So I would say that there are two parts. Skew is this semi-parametric, and it is related to this guy who is absent now. And this is related also to the talk that he made yesterday about implied volatility surface. He showed many different movies, I think 3 movies. So this skew is related to the one movie of implied volatility surface. And hedging is a part from finance, and this is related to my second co-author, Matthias Fengler, who is now in quant team in Saal Oppenheim. So what it is all about, it's about hedging the barrier options. So here is just a small picture how the barrier options are working. So if we have one path and another path, in a plain vanilla call case, the payoff is quite similar, but in the barrier option we defined some barrier, and if the price of the asset hits this barrier, then from now on this is no longer valid, there is no payoff. This is the case of knockout options. Of course, in Black-Scholes world you can find analytical formulas for barrier options, but there is one problem, or maybe there are more problems. But one problem is that how to price these options if you observe plain vanilla calls and you observe implied volatility smile. Which sigma should you plug into your formula? If you want to price some different plain vanilla options, then you simply interpolate implied volatility surface and plug in this implied volatility to the Black-Scholes formula, and then you have your price. But for barrier options, you don't know which volatility should you take. So should it be volatility of the barrier, or should it be volatility of strike? So there is not a good idea to price barrier options using Black-Scholes. Another problem which can arise is that, for example, for one volatility you can have for two different volatilities you can have one price, and of course it can also happen that price of the option can be decreasing functions of volatilities. So in order to price the barrier options, we use local volatility models. So the difference between Black-Scholes and local volatility models are here in this function sigma. Sigma is no longer a scalar, but just this is a non-parametric function. And the advantage of this model is that we can calibrate this function quite easily and quite efficiently from the call option prices observed on the market. This is here one way how to use it with so-called Duppier formula. For practical implementation, there is a paper by Anderson and Brotherton Radcliffe from '98, and they write how to get local volatility surface from implied volatility surface. But implied volatility surface, how you could see yesterday from this movie, from Wolfgang Hertle film, with this blue surface that is moving and this red points is not constant in time, so it is subjected to some random changes, and these random changes can affect also the price of the barrier options. So we take some artificial example. We take some barrier option with strike 110, barrier 80, some spot level 100, and calculate the price of the barrier option with two different implied volatilities. One is implied volatility observed, well, maybe implied volatility surfaces observed of the 3rd of January 2000, and another is 1 year later. And as you can see, the difference if the price is about 25%. But what are the two different implied volatility surfaces? You can see it on this picture. So this is just one slice of implied volatility surface. So you can see that once the surface is flat, more or less flat, once is a steep. So through the 1 year, surface moved like this. It was more or less change that influenced this 25% difference of the barrier price.
From 2000 to 2004?
This is from 2000 to 2001. I made some mistake here. It's 2001. Sorry, I made some mistake here. Then the question that practitioners ask, okay, how should I hedge my portfolio if I write some barrier option, this knockout puts or knockout calls? How should I hedge my portfolio? So first of all, you need to make a delta hedge, so you need to hedge against your changes of the underlying, but additionally, you need to implement hedge against the changes in volatility. So the standard hedge is the Vega hedge, when you hedge the changes with respect to changing on volatility. And in Black-Scholes world, you have one volatility parameter, but in this local volatility models, the volatility is the whole surface. So the standard approach is that you move your implied volatility surface up and down, and based on this, you calculate, well, so-called up and down Vega. Our idea here is that, okay, but implied volatility surface can have more complex movements, so it's not only just up and down, but it can also make some skew changes. So let's try to study how hedging performs when we, instead of hedging only up and down movements, we also hedge different kinds of movements, so this skew type of movements. And now we come to the great model from yesterday. So we come to our PSFM, and we apply this model to the implied volatility, surface dynamics, and estimate these basic movements, these basic functions, and based on this estimation procedure, we try to refine hedging of barrier options. So this was motivation of my talk. Next, I can shortly recall this dynamic semiparametric factor model. I will tell you about hedging, show some results, and maybe some conclusion. So this model we have seen already yesterday, so I don't want to stop here. In this work we use the kernel type estimation, so this was first implemented by Matthias Fengler and Wolfgang Herdle and Enno Mammen in a paper from 2000, well, it is published 2007, but firstly it was written 2003, and it is published also in a book of Matthias in 2005. We estimate with three factor functions on some range of moneyness and maturity, and there's just technical reason that in one direction in maturity direction we took increasing bandwidths. These are our functions. So this is the M0 function, so this is not dynamic, this is time invariant, this is first dynamic function, second and third, and we also got our time series, but, well, quite important stuff is here how these dynamic functions influence implied volatility surface. So this is the type of the influence of the first function. So you can see this is more or less up and down. It's not exactly up and down everywhere, but it reflects these up and down movements or up and down type of movements. And the second function reflects this kind of skew changes. So now I come to the hedging part. How do we want to implement this new type of hedging? We call it beta hedging. So in order to hedge some portfolio, you need to first get Greeks. That's why we calculate our own Greeks, so-called beta Greeks. And in practical implementation, you can see that this is a option price with surface shifted a little bit or skewed a little bit up and down, divided by 2 times delta beta. So this is very standard way. What?
How do you compute option price with your model?
We compute option price with local volatility models,
But how do you do it?
with PDE. So if you have local volatility surface, you solve partial differential equation, and then you have quite efficient algorithm to calculate barrier options in local volatility model. So this is the standard industrial vega. So this is the Greek of the up and out changes as a function of spot for the barrier, which is 5,400, and strike 7,425. And this is corresponding beta 1 Greek. So as you can see, this is a very similar shape by inverted, but in our case it doesn't matter. Then we have also beta 2 Greek, so the shape is a little bit different. Maybe here is the same near the barrier, but have different size near the spot. So how do we want to hedge? So the first and maybe the most important thing is how much different portfolios should we buy. So if you hedge norm in Black-Scholes world, if you hedge, yeah, Michal.
You said that you use 3 functions in your balance.
For our estimation and for this paper, we make so initial work only with hedging this up and down movement and the skew. And the third function, as you can see here, is more or less a term structure movement. So it is affects changes with respect to the different maturities. So if we then will jump to maybe more complex portfolios with different options, then in the very similar way we can implement these M functions. But here I believe that this is just the same type of changes and this first function. Okay, so if you remember the classical Black-Scholes approach, then you can build a hedging strategy with asset and with appropriate number of bonds. But if you go to and if you start hedge more complex derivatives, then you use mainly plain vanilla call or put options in order to hedge. So here we will use 2 hedging portfolios, HP1 and HP2, built from plain vanilla call options, and we calculate the sensitivity of our barrier option with respect to first factor and second factor, and the hedging ratios A1 and A2 we get from this kind of system of equations. So here this equation corresponds to similar vega hedging, and the second equation corresponds to the skew hedging, so hedging with respect to different changes of implied volatility surface. Now the question is, what kind of portfolio should we take? So for first portfolio, and this portfolio should more or less be sensitive to the up and down changes, this traditional one, we choose at the money plain vanilla options. And for second portfolio, which should be somehow very sensitive to the skew changes and not so sensitive to the level changes, we take so-called risk reversal. So this is long call and short put with different strikes. And of course, at the end, we also apply some delta hedging. So we hedge with respect to the changing of the underlying. So once more, how can it look like for the down and output. So this is the payoff of down and out barrier option. You can see here this is the barrier. Then first we build the hedge against the volatility. So this is the risk reversal. Here is at the money call option, and at the end we make some delta hedging. So what we study here is some kind of empirical studies. We calibrate our DSFM model to implied volatility surface, also dynamics on implied volatility surface, and we study the hedge of knockout call and knockout put with this barrier and strikes with maturity 1 year. So each day we just start one position with these parameters, and we keep this position 1 year and see what happens if we use different hedging strategies. We compare the skew hedging, so when we use beta 1 and beta 2, so the skew and let's say our level, this adjusted level, with hedging when we use only the classical way of hedging the changes of implied volatilities. What is our aim? Our aim is to reduce the hedge error, and in a perfect case we can replicate the option. So in Black-Scholes market you can replicate your call option by buying delta of stocks and appropriate number of bonds. Of course, in reality it's impossible, but the smallest variation of your hedge portfolio, then the better is hedge, in fact. So what we compare is our knockout option together with hedge portfolio, together with money, and we norm with the underlying price when we establish our hedge. So these are our results. Mean of the hedge is more or less 0, median as well, and if we look on the standard deviation, so you can see that in Vega case, even if we look on our adjusted Vega, so our types of up and down movements, we are here a little bit better, and if we look on skew changes, we also improve further. This is the case of puts. You can see that standard deviation from Vega and beta 1 was very similar, but if we include additional hedge, we can improve these results. Maybe some picture how this hedge behave in time. So if we plot here time to expiry, so maybe this plot should be inverted, then with time it goes like this, but with time to expiry, so the maturity is converging to 0, then it goes from right to left. Then you see that this beta 1 and beta 2 hedge is below this 2 traditional only level hedge in case of calls and in case of puts, but there is one bad story that at the end of holding of our portfolio there is a great delta or gap risk that we cannot hedge with volatility hedges, so the whole hedging error at the end makes them very hard to compare. So here the hedging error with 3 different strategies is not so different as if we stop our hedging, let's say 100 days before expiry. Okay, thanks a lot for listening.